So we'll get started. So in the last class, towards the end, we just wrote down the Maxwell's equations, okay, in the time domain. All right, it consisted of two Gauss's law divergence equations and two curl equations, which talked about the coupling between the electric and the magnetic fields. We also saw that when we are writing in time domain, there are a few quirks. All right, you have to be clear about the constituent relationships between B and H, D and E. In the most general case, epsilon is a function of frequency, so it is also a function of time. Mu is a function of frequency, it is also a function of time. Hence, the operator is actually a convolution operator, but in the simple setting, we consider mu to be not frequency dependent, right, and mu and epsilon also to be frequency independent, all right, but it still gives us thought about different kinds of materials which are possible with respect to space. This is the temporal dependence of epsilon and mu, but with respect to the space you could have isotropic media, anisotropic media, all right, and then frequency independent and frequency dependent. These are the broad categories of materials, and now we are assuming that we are having an isotropic medium that is frequency independent, and vacuum ticks both of these boxes. Okay, so it is safe to assume that vacuum is a material that we are considering for understanding most of the basics related to these equations. Once we did that, we also set rho equal to 0. Correspondingly, we set the conduction current to 0. Okay, and once we did this, we reduced the curl equation, right, to a wave equation, which is similar to what we had seen in the case of transmission lines. So in this lecture, the idea is going to be to establish the equivalence even more strongly, all right, so that you are able to think about Maxwell's equations in terms of telegrapher's equations and the methods to solve them, the solutions, what is the characteristic impedance, what is a forward, what is a backward wave in these cases, etc. Okay, so just establish the equivalence very strongly. So I will begin once again. Okay. The first thing that we can start with is, since we have arrived at the wave equation, one of the things that we could do is do a dimensional analysis. This is something that we had done with the transmission lines. Okay. So electric field has the unit of volt per meter. Okay. Right. You are taking spatial derivative twice, okay, taking spatial derivative twice, this means that it becomes per meter square, right. On the right hand side, I have temporal derivative taken twice, so it will be volt per meter 1 by second square, right. For this equation to be dimensionally stable, mu epsilon needs to have some units which will bring the units on the left and the right hand side to be common, right. So it happens that 1 by square root of epsilon mu has the units of meters per second. Okay. This is analogous to 1 by square root of LC having the units of meters per second, all right. So one thing is clear, that the wave is travelling with a finite velocity. Okay. Even in the case of vacuum, epsilon can be replaced with epsilon naught. Okay. This is the common notation that is used. For the case of vacuum, mu is replaced with mu naught. Okay. In SI units, the values will be 8.854 times 10 to the negative 12 and 4 pi times 10 to the negative 7, all right. And you can always calculate 1 by square root of epsilon mu, it will turn out to be a finite value or a finite velocity, all right, and that is approximately 3 times 10 to the power 8 meters per second, alright. Precise values will be something like 2.997 times 10 to the power 8 meters per second, etc. But here we can say that the velocity in vacuum, okay, okay, it is 3 times 10 to the power 8 meters per second. Okay. Now, before going further, I will also make sure that you understand the equivalence of the curl equations and the telegrapher's equations a little bit more closely, and there are some subtle differences, and these subtle differences has to be clarified now itself. Okay. So, we will take the first curl equation, right. So, I will write down del cross E, right. Del cross E is minus dou B dou T. I will start with this equation. To be clear that we are writing this in the time domain, one could simply use, anyway you are taking derivative with respect to the time on the right hand side. So, it should be clear that we are writing this in the time domain, but we are assuming some property of the material. The material that we are assuming is isotropic frequency independent material, and let us just directly say that we are going to be assuming vacuum. Okay. In the case of vacuum, there are no free charges present, as a result of which there is no conduction current density present. So, rho is going to be equal to 0, J is going to be equal to 0. Okay. Now, there are some quirks in the way we write this equation. Let us start with the left hand side. First of all, we would have noticed that there is vector notations everywhere. Okay. Del is also an operator, but it is a vector operator. Similarly, E is a vector. Now, one may remember that back when we were dealing with transmission lines and finite difference technique for calculating voltage in a capacitor, we started with a capacitor that was shaped like a cup with a lid on top of it. Okay. We calculated the voltage, and at the end of the program we also calculated the electric fields. One of the things that we noticed in that program was that the electric field was going from top to bottom, sure, but it was also curving towards the sides. So, in a two-dimensional plane, in order for you to describe the electric field, you needed at least two components, Ex and Ey. Then only you can describe the direction of the electric field in that diagram. So, which already tells you that we will have to deal with some Ex, Ey, Ez. Okay. Now, in the most generic case, the electric field has components in all Cartesian coordinates. Okay. Can be written as okay. So, where x, y and z are the unit vectors in x, y, z Cartesian axis. Okay. Ex, Ey, Ez are the components along x, y and z. Okay. This is the way one would describe an electric field, and that means that the left hand side becomes much larger than what we would have expected. The second thing that we have to see is this del cross E operator and its consequence. Okay. In the case of transmission line, we had assumed the direction of the wire to be a z direction. We assumed that the propagation of the voltage and the current wave was in the z direction. Voltage is a scalar, does not have any direction associated with it, and current is also a scalar quantity. So, these we did not consider too much about voltage and current, etc. But the direction of propagation was along the wire, and we fixed a coordinate system along the wire to be z direction. The problem now is we do not have any wire, okay. But we can begin with the simplest case. Let us assume that the wires have vanished, but the direction of propagation is still z. Okay. This is a first step that we have to make in order to understand this curl equation a little further. Let us say that the direction of propagation is z. Okay. I have put z, I have not explicitly marked plus z or minus z yet, okay, and there is a reason, right. because the wave equation solution will have a superposition of a forward and a backward wave. The forward wave will go along plus z direction and the backward wave will go along negative z direction, alright. But for now we are dealing only with one curl equation. Just to keep it simple, I am just marking this direction of propagation to be z, alright. But particularly you can say that I am starting with, let us say, plus z. Okay. If this is the case, alright, the left hand side is del cross E. So, we can write down the cross product between del and E. So, I can write this down as I j k dou by dou x I have to find the determinant of this matrix. Okay. Now, one of the things that we have to be clear about is, if the direction of propagation is z, we assume everything to be uniform in the x and in the y directions, okay, which means that the uniformity in x and y directions mean that there is no derivative present. If you take a derivative, it will become equal to 0 in the x and y directions. So, the first and foremost things that we can do is, assuming that the direction of propagation is z, we have to cross out these things and make them equal to 0. Okay. This is the first step. The next step that we can do is, we have to pick between Ex, Ey, Ez or a combination of everything. Okay. We can say that let us, for sake of just picking something, right, if you did pick direction of propagation to be z, okay. Now, we want to estimate which of the electric field components can exist and which of them can produce a magnetic field on the right hand side. There are not all the options, you cannot have Ex, Ey and Ez, and I will show the reason why. Suppose you did pick the direction of propagation to be z, and suppose you think that the electric field has a z component, okay, and let us say the electric field has only the z component, okay, it does not have any x or y component, which is the simpler cases, right. What one can do is, you can mark this to be 0, 0 and Ez, right. If you did that, what will happen is, when you are trying to find out the left hand side, you will have I times 0 minus 0 minus j 0 minus 0 plus k 0 minus 0. The left hand side becomes 0, and consequently you can say the right hand side also should become 0. The right hand side is your derivative of magnetic field, which means that this spatial change in electric field having only a z component is not creating any time change in your magnetic field. Okay. So, this is not a possibility, the simplest case. Okay. So, when your direction of propagation is z, it is incorrect to choose z in the simplest case. Okay. And we are dealing with something analogous to transmission lines. Later on we will see full vector expression for electric field and try to see how we can solve them. But for now we are considering that electric field is going to be along one Cartesian direction. Okay. So, that means the option is not to choose Ez, alright. So, if the direction of propagation is going to be z, you can cross this out. Okay. Then you have a choice between Ex or Ey. Both of them will give you non-zero magnetic field on the right hand side. Okay. So, both of them are valid, but just to make our job easier, we will say that electric field has only an x component. Okay. Let us say that electric field has only an x component. So, what we are doing now is, we are forcing this to be 0. Okay. Okay. We are forcing this to be 0. So, we are creating some electric field which has only x component, in other words. Okay. Now, if you take the left hand side, right, so this will become I hat times 0 minus 0 minus j hat, okay, times 0 minus dou by dou z Ex plus k hat 0. Okay. So, what I have now is j hat, which gives me that direction dou Ex by dou Z. Okay. So, I started with an electric field that has only an x component. Okay. Del cross that electric field gave me a j hat dou Ez dou Ex by dou Z, okay, which means that the right hand side should have a unit vector in the y or the j direction here, right. So, now that gives me an idea about what happens with minus dou b dou t. Okay. So, we can write down minus dou b dou t, right. So, we can write this as minus mu dou h dou t, all right. This means that mu is a constant for all our cases. We have considered isotropic frequency independent material. So, it is a constant, all right. The only thing that can have any vector property is the magnetic field itself. That means dou h dou t should be having some j, all right. It has to, for the equation to be stable and have equal equality, you should be having the same directions pointing, all right, which means that the magnetic field can only have a y component. Okay. So, this means that your magnetic field will end up having a y component. So, if your direction of propagation is going to be fixed to z, electric field will have, suppose, only an x component, magnetic field will automatically start having only a y component. Okay. Okay. This is something that we need to get used to. In the case of voltages and currents, we did not deal with any directions, but here we need to deal with directions, etc. This is something that you will have to keep in mind. You should never use dou Ez by dou Z for a Z direction propagation, because it does not create any time varying magnetic field, right. The system is now clear. I am going to be having Ex Hy propagation in the z direction, all right. Okay. Now, if this is the case, my curl equation actually does not have any derivatives in x and y, dou by dou x, dou by dou y is just 0. So, I will just end up having dou Ex dou Z. Okay. So, del cross E became dou Ex dou Z, right, and I have here minus mu dou Hy dou t. Okay. All right. Now, let us just go back to our notes and write down what equation we originally had for our transmission line. Okay. So, I will just write down the transmission line equation on the right hand side to just establish the equivalence. Okay. I had dou V by dou Z is equal to minus L okay. So, it is exactly the same. If you just change the variables, it is exactly the same. What it means is the computer programs that you have written already are going to be the same to solve the Maxwell's equations. Okay. You do not even need to change the variable, because it is just the name of the variable, does not say anything more than the name of the variable. So, in essence, the program that you have written in the past actually solves Maxwell's equations, actually solves wave equation for electric and magnetic fields. It is just that you just call it by different names, that is it, all right. So, its equality should be very clear. Now, if I want to write down the other telegrapher's equation, I will begin with the other curl equation that I have. I will use the same rules, z direction propagation, which will mean that I can have only Ex Hy or Ey Hx, etc., but I am fixing Ex Hy over here, right. Ex Hy then I will end up with another equation. I will write that equation down, right. Okay. I will end up with dou hy dou z is minus epsilon dou Ex dou t. The equivalent equation that you saw in transmission line will be dou I dou z is equal to minus C dou V dou t. And at this point should be abundantly clear that all we are doing compared to transmission line is changing variable names. Wherever a current occurs, you just changed it to magnetic field, and the unit for the magnetic field is ampere per meter, alright, you are changing the units. So, if you are making the left hand side from ampere to ampere per meter, the right hand side should change from say volt to volt per meter. So, the right hand side is becoming E instead of V, that is all, alright. So, it is almost exactly the same, alright. Now, which means that the conclusions that we drew from transmission line for telegrapher's equation and wave equation are going to be exactly the same as what we can arrive with Maxwell's equations, okay. And what could those conclusions be? Let us go back to our transmission line thing and take each quantity that we have calculated and then calculate them back and then try to denote them with different variables, so that it becomes clear that we are talking about either a transmission line or we are talking about wave propagation in vacuum, okay. That is the only thing that we can do now, okay. So, we will have some left hand side quantities, we will have quantities on the right hand side, but we have to be clear about whether we are talking about transmission line or a wave travelling in vacuum, okay. Just to make it clear, we will just mark with different variables, okay. One of the things that we can do is take the wave equation, okay. So, I will write down the wave equation for the transmission line on the right hand side. So, I will have dou square V by dou z square is equal to 1 by u square dou square V by dou t square. This is the equation that we had in the case of transmission line, okay. I want to write down this equation for the electric field. All I need to do is replace V with Ex, right. One by u square remains 1 by u square. The difference has to be pointed out. U is 1 by square root of, we are dealing with vacuum. So, I am putting mu naught epsilon naught, okay, and in this case we are dealing with some capacitances and, okay. Now, when we talk about transmission line, it is very common to use the letter U for the velocity. When we are talking about electromagnetic waves, U is not very commonly used, right, and especially when we are dealing with vacuum, etc., the letter used is C. Just we will replace some variables to make it clearer that when we are talking about an equation, whether we are talking about an electromagnetic wave or we are talking about a transmission line, okay. Okay. So, it is 1 by C square dou square Ex by dou t square. The next thing that we did in the case of transmission line is we wrote down the analytical solution to the partial differential equation for the voltage, okay. So, we had voltage is a function of position and time is equal to F plus of t minus z by u plus F minus t plus, oh, I should have written this in blue. Maybe here also I should have written this in blue, sorry about that. Okay. So, V of z comma t is f plus of t minus z by u plus f minus of t plus z by u. On the left hand side, solution is Ex is going to be varying in z and t. This is something that students have difficulty when we say Ex, it is varying in z and t. Sometimes they have confusion because they put subscript x, and then they put it as x comma t, etc. Okay, this is something that you have to remember, because I substituted Ez for a z direction propagation, it will not create a time varying magnetic field. So this is something that you have to get used to. This is a common mistake and it happens for many people. Ex varies along z and t, okay, is equal to, I am going to use the same form, right, f of t minus z by u okay. So, we are establishing one-to-one equivalence in many cases, all right. Other thing that we saw here was that the current, okay, in the forward case it was, let us just be clear about this, the forward case, okay, in the case of forward wave, right, the current was simply voltage divided by the characteristic resistance, okay. And in our previous notes I am seeing that we have written I of z comma t is equal to 1 by Lu f plus of t minus z by u. From here we had also concluded that the unit of Lu has to be that of ohms to satisfy Ohm's law. This is what we have written, I am seeing the notes, okay. So 1 by Lu has the unit of mho per Siemens, so Lu has the unit of mho or Siemens, so Lu has the unit of ohms, okay. So I will just mark this as it has the unit of ohms. Now we go to the left hand side, the equivalent of current in the case of the curl equations that we have written is going to be magnetic field, right. So we can just write this down as H y of z comma t is, say, 1 by Lu. L has been replaced with mu, all right, in our equations. U has been replaced with C, okay. Okay, 1 by mu C, okay, f plus t minus z by u, okay, which means that mu c in this case has to have the unit of ohms, because all you did was right hand side was current, all right, I mean your current was 1 by Lu times voltage, right. So you said that Lu has the unit of ohms, you divided current by space, okay, to get magnetic field ampere per meter. Same way you have divided voltage by distance, so you got voltage per meter, which means that the unit of the in between thing remains the same, okay. This means this also has the unit of ohm. So this means that we are bringing in similar concepts, okay. Now we can also write this down in a slightly different way, okay. Mu c, c is already given to be 1 by square root of mu epsilon, and we are talking about vacuum, so I will just mark it as mu naught c, okay. So mu naught c is equal to mu naught times 1 by square root of epsilon naught mu naught. This is nothing but square root of mu naught divided by epsilon naught. This has the unit of ohms. On the right hand side you had this to be Lu, so it is going to be L times 1 by square root Lc, okay. square root of L by C, we called it as characteristic resistance. Okay. So, we denoted it with RC in the beginning lectures. Later on, we also used Z naught. Okay. So, I will just put RC or Z naught. Okay. So, when we talk about RC or Z naught, we are talking about characteristic impedance of a transmission line. In this case, to just denote that we are not talking about a wired transmission line, but we are going to talk about fields, we just use a different variable, alright. So, we say that this is eta naught, Greek letter eta, subscript 0 to denote that it is vacuum and it is in ohms. Okay. In the case of vacuum, you can also extend this a little bit more. Okay. In the case of vacuum, the value of epsilon naught, mu naught are known, okay, and I have just written down the value of mu naught and epsilon naught few minutes back. Eta naught is approximately 377 ohms. So, the characteristic impedance of vacuum is 377 ohms. Okay. What this means is, if the magnitude of the electric field is going to be 1 volt per meter, you can expect magnetic field of 1 volt per meter divided by 377 ohms. That means that your magnetic field is going to be orders of magnitude lower than electric field usually. Okay. So, for 1 volt per meter electric field, which varies with position, you will be having a time varying magnetic field, okay, whose value is going to be 1 volt per meter divided by 377. So, approximately 400 times smaller magnetic field in terms of value. Effects is a different question. Okay. So, electric field values are usually high, magnetic field values in amperes per meter are usually going to be lower, right. But does not mean that the effects are the same or low or anything, but this is just to keep in mind. If you get a solution where your electric field is something and your magnetic field is higher than that, maybe you need to relook at your solution and just validate, okay, what is happening. The other thing that we can start looking into is this forward, backward, etc. In the case of the transmission line, the forward wave had a characteristic impedance of Z naught, backward wave had a characteristic impedance of minus Z naught, because the current flipped its directions in order to account for the direction of propagation. Same things will happen here. If you run the simulation, whatever we had before, and assume that whatever you are doing is with electric and magnetic fields, you will get exactly the same. So, there is no harm in thinking that whatever we are seeing here is actually transmission line. So, you could model vacuum as transmission line, air as transmission line, anything which does not have wire, but you have a source and a receiver, assuming some condition, for example, only Ex, only Hy, direction is Z, etc. You can safely consider them to be transmission line, and you know what to expect from a wireless transmission system. Okay. And to be more complete, I will just write down both the forward and the backward case. Okay. So, here I had V of Z comma t was V plus of Z comma t plus some V minus of Z comma t. In the case of transmission line, again I should have used blue, keep forgetting this. Okay. And the current is I of Z comma t is equal to 1 by Z naught. Okay. We had V plus of Z comma t minus 1 by Z naught V minus Z comma t. Okay. This is for the forward and the backward waves put together in one term, alright, and you could write down the equivalent by merely changing V to Ex, okay, I to Hy, okay, and you will have forward wave of electric and magnetic field and a backward wave of electric and magnetic field, okay, which also means that we could start looking at impedance, reflection coefficients, okay. So, even in the case of your homogeneous isotropic medium, if it is terminated somewhere, okay, with a load is usually going to have its own value of epsilon and mu, alright, it will have its own value of impedance, okay. If that is the case, you can start looking at reflection coefficient for these cases, right. Then you can start looking at impedance matching for electric and magnetic field. Then you can start to think about quarter wavelength transformer for this, alright. Whatever you could do before, you could do here, alright. But in order to be complete, I will go over a few of these in detail, okay, and leave the rest for you. For example, I do not think I will be doing bounce diagrams for this, okay, because you already know how to construct a bounce diagram, alright. But you can be sure that in the case of transmission lines, one of the things that we saw was the use of bounce diagram was, suppose you had an abnormal termination of your transmission line somewhere, you can expect a reflection or a bounce, alright, and from there you can figure out from the time of flight of the pulse how far away, and depending on the sign of the voltage that you are having, whether it is a short circuit, open circuit, etc. The same thing can be done here also, alright. If you are trying to send an electromagnetic wave through vacuum and there is an abnormal thing happening there, there is something that is blocking that and you are getting a reflection back, you can tell where the object is, okay, and you can tell the kind of the object also, maybe equivalent of short circuit and open circuit should be something over here, okay. So, whatever was possible there is possible here. So, this process where we estimated the place where the abnormality is in the case of transmission line was known as time domain reflectometry. Just means that in the time domain you measure the reflection. Two things you will measure, one is the time it took for you to get this pulse back, and the other thing is the sign of the pulse itself, okay. The same way you could do it here, and this would be just known as optical time domain reflectometry or electromagnetic time domain reflectometry. That is it, alright. So, the equivalence should be clear. The fear of Maxwell's equations should go away. The most important equations are the two curl equations, and for us the two curl equations are just two telegrapher's equations, okay. But then what about the Gauss's law? Why is that plugged in? Why are there two more equations, and how do I draw analogy between that and the transmission lines? Could be a question to ask. The answer that I always give is, do not worry about it for now, okay. Those are known as implicit boundary conditions, okay. We will get to that a little later. Drawing straight analogy for everything is going to be a little bit tedious, not impossible at all, okay. However, at this stage you have to worry about the two curl equations. The curl equations are the only ones that give you a relationship between electric and magnetic field. Remember that the two Gauss's law do not have electric and magnetic field on left and right side, so they do not give you any coupling, okay. I will stop here. In the next class we will write the program also, okay, for the three cases. Now that we are proficient in writing these programs and we also have a base for writing these programs, we will try to make some programs for the wave equation. We will also try to solve the telegrapher's equation, which is Maxwell's equation using two curl, and then try to understand the boundary conditions and what they could mean. What is the equivalent of a short circuit when you do not have a wire? What is the equivalent of an open circuit when you do not have wires? Okay. And what is a reflection coefficient in this case? Is the reflection coefficient going to be real, complex? I think we know the answer. It is going to be having a real part and an imaginary part, etc. So, we will look at these things, but with a little bit more detail. Right. So, I will stop here.